volumes and Symplectic.
Yeah, you made it. Good. Okay, thank you very much. It's a pleasure to be in Florence always. Thank you very much for organizers for invitation, and I'm really enjoying my stay in Florence. So I will talk, it's about sort of series papers, and it's a project. As you can see, I work mainly with Italians, and it's particularly a pleasure to work. There is this minor Russian scientist here, but otherwise it's Italians mainly. And there is one also minor French person over here. So it's actually the old problems we started to look. It's came from totally different projects, but then we came back and started to study basically certain very classical problems about calculated volumes, and then it developed so on. So the project actually, the whole project is extremely technical, and this is experimental math with special function, etc. But I will try to stay away from this, but I will be happy to answer any technical questions. But it's a project which is driven by hardcore calculations, actually, which is sometimes missing in our fields. So the outline roughly is the following. So first, quarter of my talk, I will talk about basic stuff, geometry. So we want to calculate something on the manifold, the volumes, etc. And generically, we want to cut it in a particular way. And of course, for us, it's obvious that if we cut, the manifold into pieces, then the volume of the whole manifold is equal to sum of the volumes, etc. But in a way, this is very little, structure. So we add more stuff. We add some actions, torus actions. Then we go to equivalent volumes. So I will, again, outline you roughly this machinery. And I will concentrate on the toric examples because calculationally they're very controllable. And then I will introduce to you this notion of symplectic cut. So it's basically a very nice way of cutting symplectic manifolds in pieces. And my whole thing would be to try to convince you some, in a way, obvious fact that these two things are very compatible. And another thing which I will tell you, one of the messages is that if you want to study compact manifolds, you have to study non-compact manifolds. This is very important because they come together. Then I will switch to quantum volumes. And there are two definitions. And please ask me, I can go either as a mathematician or I can go as a physicist. So quantum volumes, it's basically genus zero closed Gromov-Witten invariance counts in appropriate way, or it's even with equivariance, it's more refined count of what's called quasi-maps. And I can look as a mathematician to this as some solutions of Pickard-Fuchs system with quantum cohomology. Or if you're a physicist, I can look at appropriate GLSM, it's gauge linear sigma models. Okay? And the whole idea then would be basically to tell you that if an appropriate way I'm trying to apply this cut stuff to the quantum volumes, then what is going on? And surprisingly, actually, you will recover genus zero Gromov-Witten invariant. So the whole idea is that closed and open stuff are sitting in the same package. You just have to unwind this package, and it's very, very geometrical. So in this paper, we presented basically this conjecture with three non-trivial examples, explained everything, and there are two more technical papers are coming. One is related to mirror symmetry, and another with a lot of technical proofs, etc. Please feel free to ask things, and again, I will try to stay away from a lot of technical calculations, but of course, I can tell you them. Good, so the volumes. So typically we have a manifold, compact, right, M, and if I give you a volume, right, it's a volume form, it's no way vanishing form. You calculate its integral over M, and then something, very stupid you can do, you can cut manifolds appropriately with whatever orientable boundary, you add some words. This would be, I don't know, M plus, M minus, and then you can say, oh, I can calculate my volumes like this, right? So in principle, if you put on the manifold symplectic structure, you put in a top power symplectic structure, you can repeat the same story, and there is not much structure so far. What you can start to do, and this becomes more interesting than actually, so let's put more structure. So first we can go to symplectic manifold. Symplectic manifold. And of course, you know, on symplectic manifold, it's not a big deal, but your volume form will be, if it's a 2n dimensional manifold, then you can write a volume form as a n, etc. But again, I mean, cutting, there are no actually a reasonable notion of cutting by itself. Next thing what you can do is the following thing. Imagine that we have some U1 R action on our manifold, on symplectic manifold. Okay? So let me say that these guys are given by a collection of vector fields. And then what I can do do upgrade. So let me say that my action is Hamiltonian. So I have my omega plus dHA. So this is Hamiltonian for every action. And what I can do is the next very natural calculations you can do is the following things. So this is what we would call equivalent volume of the manifold. You can write on M the following object, E omega, well, you can decide about signs, sometimes A. Okay? So this would be a next upgrade of this calculation. So what's important that if you start, there are a number of issues here. If you start to expand this guy, is that a priori what you will have terms, for example, omega n 1 over n factorial E minus EA, HA, etc. So a priori this will a non-trivial function of epsilon, right? So what's good is, in principle, there are this famous, you know, Distelmer-Heckman type of formulas, Atia-Bott. I think there is Vernier formulas. Basically, what I can write to you, I can write this as a sum of fixed points. I evaluate my Hamiltonian at fixed points. Okay, and then here I have to write certain determinant of my linearized action of vector fields at a fixed points. For the sake of simplicity, I assume that everything is isolated. Okay. So what's important thing that this object is a priori depends on epsilon, and there are more structures here. Of course, what you can see if my manifold is compact, so if it's compact, then if I just can put epsilon to 0, so if I look at volume of epsilon equal to 0, this is just becomes 1 over n factorial over m omega n. So this is just becomes ordinary volume. If it's non-compact, of course this object is well defined, but you cannot, this guy is not well defined. So a priori, generically, so for the compact guy, what you can say that volume of epsilon, it has Taylor expansion around epsilon equals 0. For non-compact guys, you would say that this is generically, will have a Laurent expansion at epsilon equals 0.
Sorry, HA is just a function?
HA is a Hamiltonian, yeah. So you have a symplectic manifold, you have a Hamiltonian action, and then you know to calculate this object. There is this type of theorems you can calculate, etc. And then you get a much richer object. So the question which we are going to discuss in a moment is that, in principle, right? So for the volumes, I cut things, and basically I have to think about rentability. Then in this story, the question which I want to discuss is how to cut equivalent volumes. So at first, problem should be very simple. I have a manifold, I have equivalent volume, then I have a prescription. I cut it in a particular way, and equivalent volume of whole manifold equal to the sum of, two manifolds. Right. So let's try to put more structure on this and make it much more calculable. So of course you can wonder. So I will be very, very, quick, but you can wonder how you actually calculate this integrals, because even if I ask you to calculate it for S2, you have to work much more. So there is this non-trivial thing is that we will concentrate on Euler quotients. So basically, generically, I will take Cn and U quotient by U1R, right? So what I will do is the setup is the following, that I will have my moment maps. Mu A is equal to QAI zeta I square equal to TA. So I have my moment maps. So this is just charges. So this is typically called charge matrix. So to guarantee that this is smooth manifold, you have to put certain coprime conditions on the matrix Q, okay? And so you go at 0 at this level of these guys, and then you quotient by U1, and this would be, whatever, some Euler manifold. Now, this Euler manifold generically depends on the values of T's. So there is this things which is called chambers, depending. So for given values of T, there will be some open neighborhood. If you go sort of too far away, you may change topology, etc. So a priori, the topology of this guy depends on the region where your T is aligned. So typically, it's called chamber. Okay, so what's non-trivial to calculate these guys is the following story. So I don't know if you guys remember how to calculate the volume of P1, but the easiest way to ask students to calculate the volume of P1 is the following. So what is P1, right? So you remember that P1 is just a C2 divided by U1. So your charges would be 1, 1. So my moment map is equal to zeta 1 square plus zeta 2 square minus T. So to calculate the volume of P1, what you do something very simple. So you try to write a volume of C, which doesn't make sense, of course. And then what you do, you just put here a delta function for the moment map. So I will put indices down here, okay? So the idea is that, of course, and this is integral over C2. So this is actually the simplest way. I mean, you can do it for projective space and stuff like this. So the idea, of course, the delta function goes you to 0 level of moment map, which will be S3, but the measure is invariant, etc. So up to factors of 2 pi, it will give you exactly volume of pi 1. Now what you do here, to go here, you actually do this upgrade. So you put this minus epsilon 1 zeta 1 square minus epsilon 2 zeta 2 square. So this would be equivalent volume. What's non-trivial is the following, that these calculations on Cn, it's exactly the same as I will do actual calculation on P1 with a Fubini study metric minus whatever H. So these epsilons are not exactly those epsilons, it's their linear combination. But so in reality, the statement is the following. So let me just tell you briefly. So if you want to calculate equivalent volume of this manifold, it may be compact or non-compact, what you have to do is the following. You take the integral over your Cn, you put enough delta functions, and you see why do you need these factors, because this is compact example. If it's non-compact, you need these factors to regularize your things at infinity. Okay, so let me just give you a rough idea how it looks like. So if you want to write this thing, and again, here, for example, right, if you ask the student to calculate this delta function, you can do two ways. Either you, just perform, you go to whatever angular coordinates, etc., and then you just have to integrate basically over momentums here and resolve it explicitly, or you try to do something else. You try to represent these functions as whatever 2 pi I phi zeta 1 square plus zeta 2 square minus t, for example, minus I infinity or plus I infinity. So I can put the things here, integrate zeta, and get some contour integrals in phi. So if I write it in general, then the story, so let me denote this object. So this would be my equivalent volume, which depends on the values of t. So generically, it will be the following. It will be integral over Cn d to zeta I product I from 1 to n. Then I will have these regularizing factors, epsilon I, zeta I, square I from 1 to n. And then I will have many integrals for every function, d phi a over 2 pi I a from 1 to r. This is my quotient. And then I'm just writing minus I plus infinity. Then I will have here phi a. And then I will have q a, sorry, other way around, a I zeta I minus ta. So I assume summation of all indices. Okay? So this is a calculation of the volume. Now, what you will do now, it's integration over zeta, it's a Gaussian. You can do the integration over zeta, and what you will end up with the integral, which looks as follows. A from 1 to r, d phi a over 2 pi I, and then you will have here e phi a t a, and then you will have here, well, basically a product, I from 1 to n, epsilon I plus qi a phi a. So you can do it for this integral, so it's very easy. So then, of course, the question is that how you choose the contour, and this goes back to 90s, so there is this Jeffrey-Kirwan prescription. Basically, you can track down. So this integral is convergent with appropriate assumptions about epsilons. You relate to these guys, so a priori, your contour in phi plane will run like this. Then you will have poles here, you will have poles here, and depending on the values of t, you have to choose your contour appropriately, and you pick up particular poles. And Jeffrey-Kirwan gives you prescriptions, and they prove the integral. They prove your theorem that it's coincides with the original guy. Okay? So this object, of course, exists on the market for, I don't know, many, many years. And there are a lot of nice geometry here. You know, mathematicians like compact manifolds, we like non-compact, etc. But it's a very well-defined object. Okay? So let's go back to the problem I wanted to discuss. So now, what I want, so this is the object for these manifolds. So I want to cut manifolds. And the correct notion is symplectic cut, which was introduced in 95. So there is a good formal definition you can look up. What I will do for you, I will do the example that you understand what's going on. So as example, let me tell you a very simple space. So I have C2, right? What can be simpler than C2? Now I would think about C2 as, basically T2 vibration over this part, right? So I have this coordinate, so I'm thinking that whatever my pi I is equal just to zeta I square, and I have my omega, and you can represent your symplectic form as a d theta I, which dpi sum of I. So here that too. So you have a T2 fibration, and when goes to the boundary, it degenerates. Okay, so far so good. So now, of course, here I have a lot of different actions, and of course I can look at particular diagonal action U1 times C to C. So I'm just looking at diagonal action, so both zetas are rotated with the same phase. Okay. So then I can take the following moment map, zeta 1 square plus zeta 2 square minus C. So this would be a question of the following plane, right? So this is C, C. So now just let's think what is this. So this guy by definition is S3, right? If I look at this region, right, there is another region when I will look that my, so another region which cuts me manifold would be this one, less than C, right? It's just 4 ball. Of course, another region outside of the things, right? So I'm taking S3, I'm cutting this, and then there is another region, 2 square more than C. This would be topologically S3 times R. The problem, of course, this cutting is, what's bad about this cutting, of course, I would like to take to me, C2 is a symplectic manifold. I would like to cut and get symplectic manifolds, and that's what symplectic cuts are doing. So in a way, what I have to do is the following thing. So on the boundary, my symplectic manifolds, I have to quotient by U1. So when I'm drawing these things, what it's very natural to do from toric geometry is the following things. I would like to glue my C through the manifolds which I have here and here, but I would like along this line, right in toric diagram, basically my circle to contract, right? When circle contracts here, I mean on S3, I will get just P1. Then here I would like, in the bulk, keep the same manifold, but I would like to construct circle along the boundary. So I want to take a 4 ball and construct circle along the boundary. I want to take this part of space, S3 times line, and construct circle along the boundary. And that's what give me a symplectic manifold to glue it. So the easiest way to describe it is the following. So again, remember that S3 by U1 will give me P1. Then now, how do I describe this region? The best way of to do is the following thing. So I take my manifold C2 and I add some dumb C. And I extend my action, so I have my moment maps plus W square. So this is W, and this would be equal to C. So I can put sign plus and minus, so C2 plus C. So I'm doing now mu plus W, sorry, minus W square equal to C. So now if you stare at this equation, what it does is the following. When I'm W equal to 0, I will get mu equal to C. I'm coming to this boundary. Okay, so basically what I'm doing is implementing this quotient. When I'm quotienting U1, it's exactly like taking 4 ball and contracting boundary. Okay, here it's external space, so here's another inequality, because when I remove things, you can see that I can identify all points. When W is not 0, I can identify points basically to the space inside. Okay, so what's upshot of this operation? The upshot is the following. I get the following thing in this simple example. So I'm taking for you a C2, and I'm now, if you think what it is, so this is a quotient of C2 times C with this charge is 1, 1, 1, right? So this is just P2. So I'm gluing P2 along P1. The charges here are the following. This is a 1, 1 minus 1. So again, you have to remember that this is O minus 1 bundle over P1. Geometrically, what I'm doing, I'm cutting my space, and I'm just contracting, the boundary. Now, this is gluing, so symplectic manifold C2 is glued out of P2 and out of this symplectic manifold, which is just O minus 1 bundle over P1. Now, you can imagine that you can do it in general things. So I can write for you more general diagrams. I will have hyperplanes, etc. So this was observed in 95, that this procedures in toric setting is just exactly like cutting, you have more complicated toric diagrams, and you would just cut in different ways. And of course, it's not the only way to cut. I can cut like this, etc. Now, what's so amazing for us? So the amazing fact is the following. So if I will look at this type of objects, okay, and what's important that, so my equivalent volume as a function of epsilons of C2 is equal exactly as equivalent volume of P2 plus equivalent volume of O minus P1 minus 1. So you keep track of all actions, you keep track of everything, and this is highly non-trivial thing because this guy has extremely simple volume in terms of epsilons. I mean, there are no quotients here. This is just 1 over epsilon 1, epsilon 2. Okay, this guy is a compact, so this would have this behavior 1 over 2 t squared plus terms of order of epsilon. And this guy, well, now you shouldn't be a genius, but you will get it, that you will get 1 over epsilon 1, epsilon 2 minus 1 over 2 t squared plus 0 of epsilon. Of course, a priori, you see in this formula, what's interesting is that, you would say it's nonsense, and what does it mean that my volume of non-compact manifold behaves as a t squared? But you see, the thing is that if you start to play this game, so if you start to cut things, glue together, you can do, of course, more complicated things. It's actually restrict your things quite severely, because in this formula, I just have to fix one thing. I will know quite a lot about other things. And of course, this formula is constructed exactly such a way that this works. But it's not only this. Any questions so far?
You presented the equivalent volume at the last step, right?
Mm-hmm.
You didn't go all the way to a sum over fixed points.
It's equal to fixed points, so this is not true.
That would be the final.
Right.
You're not using that fixed point formula.
I'm not using, but if you want to prove the things, this is what I invite you to do. Do it. It's not a formal thing. It's actually. This is, I think, what math people should do. They calculate integrals. You see that everything is coinciding. It's very obvious fact, but I never seen this statement in the symplectic literature. But of course, when you look sort of a posteriori, it looks as a very obvious fact. So what's important with this formula, that calculation is very efficient. You write me a charge matrix, you specify chamber, there is some machinery, you can put in Mathematica, it calculates you 100 poles, you get complicated things, etc. Everything is calculable. And, but what's non-trivial is that this is what mathematicians like Jeffrey, Kieran proved in the 90s, that this is the same. If you will do hardcore calculation of the manifold, look at symplectic form, look at Hamiltonians, calculate. So this is a non-trivial thing. That's why I'm resuming to these quotients, because, generically, I cannot apply this localization theorem and get concrete expressions. I have to work very hard. But for the quotients, you have this type of formulas explicit with prescriptions how to do it. Okay.
So the second term could be negative?
The sign is negative, yeah.
No, the combination can be negative. Can grand volumes be negative?
Well, here epsilons are just parameters. They can be whatever. They keep track of U1 actions. Okay, good. What did I want? So there is another things here which is also very obvious. What can happen is the following, right? If you look at this diagram and imagine that you start to move your line here, right? So of course, if you take a this is P1, and if you drag P1 over here, it looks like formally you will recover whole P2. And this is actually true for equivalent volume. So if you take equivalent volume of epsilon of P1, sorry, P2, right? So this is function of C. This is the same as integral of from 1 to C of equivalent volume Y of P1. Okay, so now if you want to have equivalent volume of O minus 1 over P1, you drag P1 in another direction. So you drag it from C to plus infinity. Again, from point of view of geometry, what you look, it looks very obvious. So equivalence allows you to do compact, non-compact guys, and it keeps track of the actions, and that's what you could do. Now, what's amazing is these formulas are true at quantum level as well. Okay? So let me go, are there any questions here?
Is there anything known about other terms in the expansion?
Well, not that much, especially for non-compact. So, you know, this is what we try to study. So there are, so let me just mention, not much known. I mean, you have to study example by example, interpret the things. So basically, all these objects, they encode equivalent cohomology. So they're basically annihilated by some set of differential operators. And these objects are related to cohomology. And then there is also a question is how they behave in epsilons, when there are many epsilons, etc. So this is paper which we wrote with Nikita, Nicolo, and then Michel Vernier. Basically, so if you don't like physics, she wrote appendix to our stuff trying to represent mathematics as mathematicians. So it's exactly related to these issues, how to try to extract this data if it's invariant. Again, we did not solve the problem. It's
What I have in mind, in the Riemannian case, there is this volume for take a tube, and then you expand the volume with epsilon, and those terms are probably interpretations.
I'm pretty sure he is the same, but one has to calculate. The main thing is that, you know, people, mathematicians doing for compact things, we do for non-compact that we don't talk. But then we sit down, we started to look at examples, and we understood. So actually, our original motivation was the following. People, if you go to Calabi-Gauss, people claim that they can know from algebraic geometry how to have intersection numbers, etc. So basically intersection cohomology. Our original goal was try to reproduce them by equivalent calculations, and we couldn't get it. So we had to develop machinery to see how it agrees what people did before. But there are many open questions, I don't know. I mean, one has to look at examples and try to understand what's going on. So let me go to quantum stuff. Right, so we had volumes, and in a way what you can say is the following thing. So let's do quantum volumes. Quantum volumes. So you can look them from 2 points of view. So let me first present a math point of view. Math. So let's start from the stupidest possible example, P1. So P1, I didn't try to use the integral, but if you will write this integral for P1, equivalent volume, it looks actually like this. So it's phi t, epsilon 1 phi, plus epsilon 2 phi. That's it, and then you do this integral over phi 2 pi. So the equivalent volume is exactly just taking two poles, and if you extract regular, I mean, it's regular, and the leading term will be exactly t. This is what you expect from the volume P. So now what's important in this integral is the following thing, that there are certain things, if you remove two poles, it vanishes. So the fact is that if you think of phi as an object of degree 2, and you put your epsilons as object of degree 2, then this integral implements naturally this thing. So this is the current cohomology of P1. I mean, there are some subtleties. I don't need to have exactly these two epsilons. I just can, it comes from some redundancy that it's a quotient, but let me ignore it, okay? So then there are all this stuff that you can try to deform these relations. And for example, anyone knows, so the deformation of cohomology would be this one. So I just put for you minus t. So in principle, you can put here parameter lambda, but I will, so when you send lambda to infinity, it just becomes classical thing, okay? So that's relations I can think of. So if you actually stare at these integrals and you ask which integral will implement these relations, it would be the following integral. What you have to do in the integral, so we put D. D stands for disk. It's notations from our paper. So what you do is the following thing. So you will take integral of gamma function epsilon 1 plus phi, gamma function of epsilon 2 plus phi, e phi t, d phi over 2 pi I. So if previous integral, here this is what's called Jeffrey-Kirwan things, here we just call them quantum Jeffrey-Kirwan. So there is a prescription comes again from finiteness of the integral. Now what's important that if you take these relations put under the integral, it's identically 0. So this is known as a equivalent quantum cohomology. Now, this guy automatically, so these relations, if I write in terms of operators, will be the following: epsilon 1 dt epsilon 2 plus dt minus e minus t acting on fd equal to 0. So this goes under the name as a Pickard-Fuchs equation. So there is a natural deformation. So if this term is absent, this just guys implemented this relation. This is classical equivalent cohomology. This is quantum. So this is a mathematical way of looking at this, and there are basically very natural cohomologies you can. Now, for those physicists, so you can ask what it is. So let me make a comment for physics, audience, physics. So this model actually is gauge linear sigma model. So if you take a gauge linear sigma model, so you take C2, you will take U1 field plus 2 chiral field, for example, on disk with whatever space filling brain, you can write this setup, you can calculate exact partition function, which has been done, for example, in 13 by people like Hori and Roma. You get exactly this thing. I'm skipping, of course, physically, people know that it's much more relevant for Calabi-Yaos, but in principle, formally, you will still get this stuff, okay? So this is, can be derived at least through localization. So this is basically the theory. You specify the theory, you perform exact calculations, it's into D, and this is basically one loop determinants, etc. That's what you get. Or mathematically, you can look as deformations of cohomology. Okay? Any questions? So let me just maybe tell you a few things that it all sounds simple, but so you would like to calculate this stuff. Now, since it's a deformation, so let me just impress you with a few formulas. Right. Okay, so you wrote this stuff. Then let's discuss this stuff. Again, P1 is not that interesting example in physical context. What is much more interesting is, for example, Conifult or more. So this is famous, so which is called resolved Conifult. Which is this color quotient, 1, 1, minus 1, minus 1, or geometrically this is O minus 1 plus O minus 1 over P1. So this is a very famous example. Okay? So I can write to you this F disk as, function of T, epsilon. This is just gamma epsilon 1 plus phi, gamma epsilon 2 plus phi, gamma epsilon 3 minus phi, gamma epsilon 4 minus phi, e phi t d phi over 2 pi I. Of course, classically, so if you will put a parameter classically, the leading behavior here, it will be actually, so the object, this object is, looks as, equivalent volume plus terms of order E minus T. So this is typically called semi-classical term, semi-classical. This is called instantons. So there are very interesting features appearing in this quantum world, which we don't understand, but right, now, so these guys satisfy this Pickard-Fuchs equation. Okay. So now what's important that these expansions, to write for me this expansion, it's very important to specify t, because if my t is positive, right? So switching the value of t, it's not a big deal. It's just like exchanging minus here sign with minus here signs, okay? For volume, it's very, very important. You change the poles, etc. Now, to have this expansion, of course, I have to specify if my t is positive, I will expand in exponent c minus t. If t is negative, I will expand with pluses. So if you take this function, so just imagine, I don't need to write for you this integrals. You can do things the other way around. You have these cohomology relations expressed as Pickard-Fuchs. You write them, and then you do semi-classical expansion. So these things actually looks as follows. And whoever in their life did Gromov-Witten will recognize this. So there will be semi-classical piece, and then there will be this piece, t plus Li2 e minus t minus 2 Li3 e minus t plus terms of order of epsilon. So Li3, and this particular 2, it's too trivial example to discuss, but this is exactly Gromov-Witten invariance. So these guys are all a closed genus zero Gromov-Witten. Of course, if you go to more complicated guys, you extract the things, then you get more complicated numbers, and there are mirror map involved, etc., which I don't want to discuss. Now, what's interesting about quantum volume is the following thing. So my classical volume requires me to specify in a chamber. So I have to tell you either t equals 0 or t less than 0. Okay? It's a different expansion. It's a different semi-classic, it's a different expansion. But actually what's amazing about the things, this is the same solution. So this is basically symbolically can be written as follows. So it's a particular combination of hypergeometric. So if you solve it explicitly, so this f of d, epsilon t, it's some coefficients, f21 with something, whatever, e minus t, plus, again, some coefficients, and then f21 e minus t. But then there are a lot of relations between hypergeometric. So this object, you can go from negative to positive t, and you will reproduce things totally correctly. So I don't know if it's a generic feature or not, but this object is actually defined independent of the chamber. Well, semi-classical object is defined dependent on the chamber. So here you can go and you can even ask what's the value of this object at t equal to 0, etc. Okay, so this is the story. Okay, good. So now, any questions?
So you took the Conifult,
Mm-hmm.
you described this expansion where you have a semi-classical plus this, and then you were saying that these are the closed genus 0
Right.
variants for P1.
No, for this guy, Conifult, for resolved Conifult.
So you're just presenting what the invariants are.
Yeah. I'm not telling you how to calculate. I'm saying you someone, whatever in 90s did it, or you take a mirror symmetry book, or you take it, etc. It's a generic statement. I'm not telling you how to calculate. And of course, a priori, it's a shortcut for physics ways, because to calculate this type of numbers are very, very hard from first principles. But now what I'm saying, take any toric guy, Calabi-Yau threefold, do this dance, etc., do certain things which call mirror map, and you will get all these tables which you can find in Clem's papers. Okay. Or if you go to 90s, all these people like, Pandari Pandits, they did a hardcore calculation. You construct a modular space, you do localization there, and you get formulas. But then this will be eventually the same. So I'm presenting to you like, oh, it's not a big deal. It is a very big deal. It's like, 20, 30 years of development. But the whole thing is what I'm trying to give you this simplified picture that I have a classical volume, then I have a very natural quantum deformations. I solve these quantum deformations, and these quantum deformations, if you extract terms according to certain prescription, they encode all closed genus 0 Gromov-Witten, okay? Well, it will be almost theorem. The only problem is that mathematicians like compact manifolds. Giventhal, for example, did hold the things for complete toric intersections, and the status for. So the tricky thing is the following: that for non-compact, you have to make sure how to define this, how to define this. For us, it's a theorem, but for math people, it's not. But I'm saying to you that it's a problem of math people. They don't like to work with non-compact examples. So physicists work with non-compact examples. They're physically very relevant. There are a lot of correspondences, gravity, decouple, etc., etc. Mathematicians try to go to these toric intersections. Quintic is one of the famous. So we can also write very explicit formula there, but they're compact. Yeah, of course they do non-compact manifolds, but most of the result and all this Giventhal formulas was developed for for these toric intersections. So we pointed to Clem and to these people. For some non-compact guys, so there are basically what you have to argue that the instantons don't have term singular and epsilon. There are very exotic examples when they have it. And Clem 20 years ago had Gopakumar-Waffe invariants half integer, and they said they're crazy, etc. But we understand that there are certain columns in the invariant that you cannot get it. It's related with regularization. Again, mathematicians don't like to expand things. It's not that we have very systematic science for this. Problem with Laurent expansion more than one variables is it's not clear how to deal with them. This is why we don't have vertex algebras outside of one-dimensional cases. So here's the problem. So you need the extra input to do these things. And for example, there are examples. This is local F1. This is where trouble comes. Okay. Anyhow, let me try to, in remaining 10 minutes, make another upshot. What you can ask here, okay, good, we can calculate this object, they're complicated, you can study them, etc., etc. But what if we do cut and we start to calculate, different things from the cut? So now let me do the simplest possible example, but physically relevant, C3. So C3 does not have any closed stub whatsoever, okay? And for example, what I can do is that I represent C3 by this object, right? So this is my, P1, P2, P3. And then I can do a cut. For example, the cut I can give you by the following plane. So the plane will be basically P2 minus P3 is equal to C. So it means that if it's P1, P2, P3, right? So then I would have my plane. So when P3 is equal to 0, I have P2 is equal to C here. So it's some plane which cuts. I don't know how to draw these things, but it's some plane which cuts space in two pieces. Okay. So of course, as I told you, I can repeat this exercise which I did before, but this is defines for me symplectic cut. Okay. And exactly what I told you, but I'm not going to consider things that in principle you can calculate. So the volume of C3, the volume equivalent of C3 is equal to 1 over epsilon 1, epsilon 2, epsilon 3. So you can integrate things from one side, from another side. You have to look at chambers. You see can be negative, positive. It sort of moves things, etc. But you can definitely do the things. And what you can do is basically, roughly speaking, this is not quite correct formula because you have to split it, but this basically, you can think this is the volume of this plane. So by itself, this is just, you can think of some Calabi-Yau twofold, right? So I'm taking a plane, I swap it around, and I will recover the volume. So let's do the same exercise in a quantum case. So in the quantum case, what I would like to do, I would like to say that I have my volume, quantum volume of C3, which is actually, in this case, is pretty trivial, and this is just basically a normalization thing. Again, I'm not a mathematician, but I'm pretty sure that maybe what you can define, this is what you guys like to do, you can define this equivalent volumes axiomatically. So if I assume that my value of a volume is equal to this value on certain spaces, and then I'm asking how it's consistent with cutting and gluing, presumably I can derive everything. But again, I don't want to make this statement. So this is some normalization thing. Then I would like that this would be the same if I drag my plane over the thing. So I will have this, DC. So this what I will call is, this is correspondently quantum volume for plane. Right? Or, of course, there are another natural objects I can look at part of the space. If I fix my plane, if I don't drag it, I could equivalently for you to define this guy, FD, for example, less than C epsilon, and then I will define this as a minus infinity to C, H, D, Y, C, epsilon over dy. Okay, so intuitively it's very clear. Now, of course, this type of objects I can divide, again, defined, it's in the, if you give me a toric data, there is a very canonical way, for example, to produce Pickard-Fuchs systems, okay? So if you do it, just to give you example, so this object is actually will be given to you. It's a concrete calculation. So I mean, these factors are normalization. Epsilon 3 plus epsilon 2, E epsilon 2C, 1 plus EC epsilon 1, epsilon 2 plus epsilon 3. So it's a concrete solution of Picard-Fuchs. Now, if you take these guys, you integrate it, you get this. Again, integration is de facto removing the moment map condition. But the quantum stuff, it should be also respect the things. Now, just to tell you this stuff, for example, again, you do the calculation, you get gamma of epsilon 1, gamma of epsilon 2 plus epsilon 3, E epsilon 3C, F1, 2, epsilon 1 plus epsilon 3, epsilon 3, epsilon 3, minus EC. So this is some hypergeometric. So the quantum volume from one of the side of the plane will be given in terms of hypergeometric. Now, what's the point? So there are facts which we observed is the following. To take this guy and calculate these things. So take half volume from the plane and calculate these things. C plus 2 pi I epsilon minus F of D of C over epsilon. Okay. So this is in physics called superpotential. So if you will take these guys and expand it, so again, you expand it, there will be some semi-classical pieces plus Li2 of phi minus C plus terms of order of epsilon. So now this guy is actually related to open Gromov-Witten genus 0. What I didn't tell you is the following. So there is a whole science, but I will outline is. So in principle, this symplectic cuts or particular subclass of these cuts are one-to-one correspondence with toric Lagrangians. So in principle, this result goes back to 80s that special Lagrangians, there is big class of special Lagrangians which on toric geometries can be described as some torus vibrations over planes. So you have to discuss these planes. These planes have particular slope, etc., etc. So in principle, you can think of toric Lagrangians. So there is this toric slug, which is given by, again, it's a very sort of analysis which requires time, but it's basically a fine line with a particular angle, etc., which guarantees all your conditions. And if you take a plane which passes through this line, this would correspond to the choice of slug plus framing. So this is terminology by Waffe. And our claim is the following, that if you take the symplectic cut for this Lagrangian, calculate things, and extract this monodromy, then this guy contains a superpotential. And you can extract all this data which people reproduced before. Now, what's interesting here is the following thing, that equivariance, so people, of course, in standards theory like this, and for example, there is a very efficient way of calculating the things through periods on mirror side. So you can reduce this to certain integrals on the mirror curve, etc. That's the main approach how to calculate the things. And of course, it's totally non-equivariance science. Now, what equivariants are teaching us that it's very nice here because there are very different branes depending on the region. If you see it's positive, negative, there are different phases, etc. But as you know that calculating, so this is the same function, but to calculate your monodromy, I have to specify the region. So this is not a universal formula. This is a region dependent. right? I mean, I have to tell you if my C is positive or negative, if it's more than one, less than one, etc., because the behavior can be very, very different for monodromies. But this is the same function. So this function actually H, we called quantum Lebesgue measure. So we are saying that if, you take this, for this symplectic cut, you take this quantum volume, then if you integrate over whole space, your toric space, you will reproduce closed Gromov-Witten. If you sort of calculate monodromy, this is integrated version, but you can also write differential version. When derivatives of this is related to monodromy, this H, then you will get open invariance. Again, this type of picture should follow basically from Volt's sheet, but there are no available descriptions in GLSM of this A-branes for slugs. So, I mean, in a way, we're recovering the things, etc. Now we have a proof in our terms, not in your terms, of that this is fact is general, but of course, before we had it, we did a lot of hardcore calculations actually to see. In the first non-trivial example, it's a local P2 when things become so complicated and it's not very elementary functions. Okay, I think I overrun. So I just basically gave you an idea. I didn't write many formulas. You can look them in the papers. That's it. Thank you. Yeah, yeah.
So then usually when you do that, you get a number at the end. You regularize.
No. You want to keep them as a parameters, right? So.
Regularization, usually you do get a number at the end.
Well, it's not that. Let's calculate the volume of C, right? So what I'm telling you is the following. I calculate the volume of C. This is 2d zeta minus epsilon zeta squared. And then I get 1 over epsilon. It's just infinite. I mean, how can you regularize the thing?
Usually they take, for example, 1 as the residue of the expression as the regularization and stuff like that.
No, I mean, the thing is that, of course, you can understand what I'm saying is that this epsilons keep track of U1 symmetries.
I mean, they have more information.
Right.
But I was wondering if there is a scheme to regularize, to get some regularized
No, the scheme, for example, is try to extract regular terms. But this is what we realize, that this scheme is not very universal. I mean, you have to, so all our activity goes back. There is this papers by Shatashvili, Moore, Nekrasov, and they try to calculate these volumes. So the idea was exactly you regularize. So for example, if you calculate the volume of or minus 2 over P1 with particular choices, you get this term, and then you will get 1 over T squared plus term of epsilon. Then you would say, oh, good, this is a singular term. We subtract, and this is a volume. The problem is that those guys 25 years ago overlooked that if you start to go to complicated examples, that's how a project started. It's not universal. I mean, it's very hard to, so there is basically no universal prescription to extract this term, okay? So I don't know how universal things to extract. But of course, this was originally motivated, and that's exactly what physicists did. They would say that regularized volume of this guy is this, and we ignore this. But the story is more complicated.
The whole series is the story.
Right.
Do I understand right that you're kind of saying that instead of having to use mirror symmetry and the Picard-Fuchs equation in order to obtain these invariants, like the generating function, you have a way of just immediately calculating it by kind of decomposing the toric directly and doing these integrals directly?
No, Marco, I mean, all the things are related, of course, right? I mean, you can write, that's why I talk to you, etc. It's related to, so in canonical things, you can relate them to periods, integrals on the mirror stuff, okay? So now what those guys on mirror stuff, etc. So in principle, you go to mirror manifold, you have your periods in H3, you take a holomorphic volume form. If it's period closed, you calculate something, whatever, closed period for closed Gromov-Witten stuff. If it's open relative period, you get an open stuff. That's a main technology to calculate these numbers in an easy way.
Okay, but if you're saying that you should take your toric variety
Right.
starting from something simple, then could you not just write the invariant for the simple thing and then integrate this?
That's my homework for you. I mean, yeah, of course, but I don't know. I mean, this is what I said, that I think at the end of the day, there should be something axiomatic. And another thing is, for example, I'm not clear what's interpretation of symplectic cut on the mirror side. So the technological things on the mirror side a lot, right? I'm just calculating holomorphic integrals, I re-expand it, I get Gromov-Witten invariance. Now I'm saying to you, on the symplectic side, there is very nice cutting prescriptions. I have no clue what's natural things on symplectic things, go there. But basically, there should be some operation on the complex side which somehow compatible with this, but we have no clue. And I already asked you that this period already looks crazy if you want to reproduce some of these formulas.